So welcome to lecture 28. This lecture is going to be about problem sets 8 and problem set 9. We're going to be finishing up a question on Laplacian from problem set 8 that we didn't quite finish in the last lecture. And then we'll do one of the plucked string examples from problem set 9. I just want to remind you, so I have to make an official announcement by email, but just to remind you that to continue doing your problem sets, the people in the math department are beginning to finalize the exams this week, so they'll be sent to checkers this week. But just to repeat, so this is information that you should already know. Your exams across all your math courses will be such that 80% will be essentially standard material. So this is going to be reflective of all the other year's exams. So the same structure that you can expect if the lectures would have continued at the university. So in my case, the exam that we proposed in February or in March, the exam that I sent off to the checkers in February or March, this will form essentially the 80% component. And then there's that 20% open-ended question component, which I have yet to discuss. Okay, so you can expect essentially to be examined on the spectrum of material that appears on problem sets 1 through 10. If there are exceptions, then they'll be mentioned in the study guide, but for the most part, you just treat it as business as usual. So we've covered now, we're now in the midst of problem set 9. There's essentially two more topics that remain. There's D'Alembert solution, which appears at the end of problem set 9, and then there's uniqueness of solutions, which is the content of problem set 10. Okay, we'll continue to do the lectures most of the Easter break. So, for example, I haven't just quite decided whether I want to do Friday or not, but we'll continue to take it slow. So I'll do the problem set questions that I think are appropriate, that will help you. And then we'll continue to cover those two remaining bits of material, the D'Alembert solution, and then the existence and uniqueness. Or rather, the uniqueness. You don't study existence in this course. There's one chapter, which is the maths of music, and I will cover this chapter. There's no problem set questions about it, but it's an important concept to understand, and we'll come back in the next couple weeks and then cover this material. So the learning about how we can apply Fourier series to study sound processing, so signal processing, and how to decompose music using Fourier series. Someone's asked how much bookwork will remain in the 80% question. What do you mean by that question? So what do you mean by how much bookwork will remain in the 80%? Yeah, okay, so that's right. So I have to be very careful about what I say about other courses. So I'm not going to say, I'm not going to tell you what your lectures on other courses are doing, okay? Because if I tell you something that's wrong, obviously that might come back. But I will tell you that the version of the exam that I proposed in February or in March is going to almost definitely, and if it isn't, then I'll tell you, it is almost definitely going to be that version which is going to be used in that 80%. Okay, so if there was definition at that point, or if there was a state this bookwork item that was expected for you to have memorized and to have come to the exam, to the on-campus exam prepared to cite, then it would still remain in that version exam. Okay, and you can look at last year's exam or the years before to get an idea of the question. So I won't be going back and rewording any of the questions in light of the fact that it's an open book. I think the intention of the DOS guidance is that we keep the structure as close to that original structure as possible, even in light of the fact that it's open book. That last 20%, so the 80 and then 20%, that 20% open-ended question is obviously designed for the fact that you'll be doing it open book or at home. Okay. So again, I don't want to say what other lectures are doing. I can only say about what I'm doing, and I'm not going back and restructuring the questions based on the fact that you're doing it at home and open book. So if there was a definition question, if there was a very mundane question about state this or state that result, or some result that appears in the lecture notes, I haven't gone back and changed that. Does that mean the overall paper will be longer because we have the normal exam already and another 20% questions? So you can correct me if I'm wrong, but you have additional, so you have additional time to do it, right? So the recommended length of the exam is longer than what it would have been if it's on site, and obviously this is spread out between all your other exams, and you don't hand it in. You hand them all in, or you hand them in within some time band. That's right, 3 hours. So it would be longer, obviously because of the extra question, but it's shorter in the sense that it's open book. So presumably some of the questions that you would have been thinking about, you have the ability to consult. But again, that depends on the particular content of that particular exam. Any other questions? Is it possible to get more than one exam in one 24-hour period? Will any of them be stacked one after the other, or will we be given a full day break mandatory? My impression, again, I would rather not conjecture about this because I think the procedure needs to be sorted out. My impression is that they would have to give you multiple exams at the same time, because otherwise, otherwise, I don't quite know how they would do the scheduling. I mean, if you think of the entirety of all the math students doing all the math courses, if you were to only dole them out one day at a time, I'm not sure whether that would work. Did the exam period get extended to 5 weeks? I had the impression it was 2 weeks. Yeah, so that's right. So if you examine the letter from the vice chancellor or from the DOS team, one or the other, I think it's suggested that the exam period will be extended by 2 weeks, though the intention of why they're extending it is still unknown at the moment, as in, does that mean that you'll be writing your exams later? I don't know. So it could be that you're writing your exams later, or it could be that this is to give us more time to assess you, as in to mark the exams, or it could just be to give more time in the case of special exemptions. So they've mentioned the extension of the exam period, but they haven't mentioned what that means in relation to the scheduling of your exams. Multiple exams in 24-hour period. So I don't know the details of whether you can expect to get more than one exam a day. I had the impression if you were writing exams on campus, there would always be the chance that you'd get more than one exam per day. Would it not be rare that you would not get more than one exam per day? Scheduling is a very difficult thing to do, so I don't. I mean, as always, when you're thinking about your own situation, you're only thinking of yourself, right? But obviously, there's some 10, 15, 20,000 students on campus, and they have to somehow organize this mess of exams. And I don't envy anybody who has to do the timetabling for that. I don't know anything about scheduling of when you're going to get this stuff. So we get the information when essentially you get them. They haven't sorted out the scheduling yet. So I don't know, for instance, whether the scheduling is the same scheduling as if it were on site. That information hasn't been released yet. Do I know anything about a safety net? All I know is that we've emailed the DOS team to clarify the no detriment safety net thing. They've emailed us back and said they're sorting out. The university is sorting it out, and they've given us a statement to tell you all, but I can't remember what the statement is. But the statement is essentially just hang on, and it will be clarified in the future. Okay. We wasted a good 15 minutes going through these questions, but it's good. I mean, I'm a bit tentative to answering some of these questions because it's beyond my pay grade to conjecture. That's very worrisome if I'm your main source of information. I mean, I've been meeting my student. I've been meeting the first and second years, and even my fourth year project students are always asking about how I feel about the current proposals, and I tell them, well, I tell them many things, right? The one thing I do tell them is that you have to appreciate that the math department, I think, has come up with a very good solution. So this solution of doing 80% and then 20%. When you think about the alternatives, you think about other ways of assessing. So, for instance, would we, the lecturers, have to go away and draft our own exams, a completely new, brand new exam, and how would that be done? You realize that actually the solution they proposed, the 80-20, is a really good solution that checks as many boxes as you would hope. Everyone is in a really difficult position. And I was thinking about how I would have felt if I was a student during that time. And this puts us into a very difficult position because for us, so now that I'm not a student, I view grades in a very different way than I did when I was a student. If I was a student at this time, I think I would be very stressed. And, for me, when I was a student, grades were really important, and I worked really hard in all my courses. And so suddenly to have this change in the structure, I don't know whether I would have been worried about, does that mean that all the hard work I put in previously doesn't apply? What does that mean in terms of getting really good grades or not getting really good grades? I think I would have been very stressed about it. So even though now as a tutor or as a lecturer and I talk to the students and I say, look, the world is in a difficult position and to a certain extent, you're in a better situation than if you just lost your job or even if you were doing your A-levels, if you were in that situation and you just lost your entire A-level year. So trying to frame it in the context of there is a bigger picture, and I don't think that whatever will result from the situation, I don't think that you're going to be impacted in a comparatively significant way, so you might have gotten a low first and instead you might get a high 2-1 or vice versa. So I don't know anything about the way the grades work. And so it's tempting for me to take that perspective, take that bigger perspective. At the same time, I do think about how when I was a student, obviously, I wouldn't have been thinking about it in that way. The other thing that, of course, I was thinking of was that when I was in school, so when I was 16, I suppose 16, 9/11 happened, right? And I remember, I think I was even younger, I think I was 15 at the time. 9/11 happened, and I remember, and I was in Canada at the time, and I remember it came over in the PA system that planes had crashed into the towers in the US. And we all, I was in the computer lab, and I remember going, we were looking at the news of this happening. And the one thing that I do remember is that the significance of that event was completely lost on me at the time. That it was just something that happened, and I couldn't quite process what it would mean in terms of my situation. But now, some 20 years later, close to 20 years later, that now you see how much that event changed the entire landscape of the world, right? The way that we travel on airplanes, the way politics work, the political divide that exists in different countries. You just see so much impact of that event. But when I think about how I was at the time, that impact wasn't quite clear to me. And I do wonder, so obviously you're older than I was at the time. You're now, you're in your 20s. You're all adults. And, but in many ways, you're facing a similar situation. The world is going through this change. And certainly in 10 years' time, you're going to look back and think about, I was in university at this time, I was going through this year, and then all this madness broke loose, and I had to deal with this, or I had to deal with that. Everyone had to be home and learn their lectures on the computer. And I do wonder how your mindset will change in the next 10 years. And so that's the kind of thinking that we're struggling with, right? So on the one hand, we're like, right, you're taking university courses, we're still lecturing, you should still be doing your problem sets, you should still be doing this or that. And that's like a local perspective. And so in many ways, it's important for us to maintain the grade standards and to still award 2-1s and to award first and award thirds and to encourage students to study. And that structure is important, and we feel that it's important as academics to maintain that structure. On the other hand, you're reading about all these universities that have gone to pass-fail systems, that have gone to no detriment policies and all these things, and you're trying to rectify what the consequences of your decisions will be. And that is a really difficult position that I don't envy any of the lecturers in math and the staff in the math department in the university who are having to make these decisions and to balance your happiness with what they perceive to be an important component of higher education. So that is, so I mean, keep in mind that this is the atmosphere that's around us at the moment in making these decisions and thinking about how we should do these exams, right? And these are I do think about these things when I'm trying to draft this 20% component of the question. How difficult should it be? What elements of your learning should it encourage? And also to think about your personal situation and whether it's difficult for you to study, or is it, should I just expect you to toughen up and to study on your own and to watch your courses and to do your problem sets, or do I have to back off and think, oh, actually, they're in a really difficult position, and you need to be much more sensitive to that. All these decisions that you may not think that we think about, that we do. If you want help, I'm sure you're all happy to help me. Okay, sorry. So we've wasted a lot of time, but you know what? Maybe it's therapeutic just to talk. Let's get into it, okay? Let's get back to work. I'm going to start off by actually addressing a typo that appears in my visualizer notes and in the problem set solutions that you might have. Some people noticed it right away, and some people will continue to email me about them. So the problem relates to around problem set 6 and the issue of periodic functions. And in the and this correction also appears on the errata on the website. So if you go to the website and you look at the errata, which is the list of errors or typos that have appeared, you'll see that it's been updated to include this element. So in one of the lectures, I stated that the function e to the cosine of x, I wrote, is this thing here periodic? Question mark, and I left it for you to decide, and I wrote no. And that is completely wrong. I don't know why I had that brain freeze. This is a periodic function. Okay, and you know it's a periodic function because, well, there's two ways of thinking about it. You can think about what this function looks like, and also you can think about the properties of periodic functions. Okay, so let's talk about it in terms of the properties of periodic functions. This is a function f of cosine of x, where f of x is equal to e to the x. And in this case, you can check that. I think it's a little bit better if I write this as a capital f of x. So this is my capital f of x. You can check that capital f of x plus pi, or 2 pi, is equal to capital f of x. Okay, so if I put in x plus 2 pi into here, then the cosine returns me to cosine of x. So you're returned to the original value of the function. So any composite function of a periodic function is periodic. Okay? So, sorry, any composite function of a periodic function is periodic. I think that's true. So, what did I just say? I said that if so in this case, r f of x, I've defined my capital F of x to be e to the cosine of x. And you can verify that if you shift this x by a period, then this argument, this exponential, goes back to its original value. You can also imagine what this looks like. So this is x here. You know the cosine function starts off at 1, it goes down to -1, and then it goes back to 1. And so if you feed this into the exponential, then it starts off at a value of e to the 1, or 2 point something, 2.71, I suppose. And then it goes down to a value of 1 over e, and then goes back up to a value of e to the 1. Okay, so this is the graph of cosine of x. And then if you feed this into that exponential function, you should have something that starts off at 2 point something, goes down to a minimum, and goes back up. The curves will look slightly different because this exponential will alter the shape of this, but it's still a periodic function. Eventually, this cosine of x will repeat, right, after 2 pi. And then it's fed back into the exponential, and then that also repeats. So this is indeed a periodic function. Okay? The reason why I had the brain freeze, and I wrote this, so if you go to the scanned visualizer notes, I think it's around lecture 16, you'll see I made that mistake. The reason why I had that brain freeze is because in the problem sets, bring up the problem sets for you now. In the problem sets, if you refer to problem set number 6, it asks you whether this sine of e to the minus cosine of x squared function is periodic. Okay, and so the sine function is periodic with period 2 pi, and so the question is whether this function here has a period which is commensurate with 2 pi. And this e to the minus cosine x squared function is not periodic. Okay, and the reason why e to the minus x squared cos of x squared is not periodic is because cosine of x squared is not periodic. There's two ways for you to figure that out. You can figure it out algebraically. So you can ask yourself whether it's possible to add some period L to the argument of the cosine of x squared so that it cycles back to cosine of x squared. And this essentially you just have to stick in x plus L squared is equal to x squared plus a multiple of pi. And you can show this can never be the case. The easier way to illustrate it is just to check what it looks like. Or you might want to have done this before you try to prove it. So if I just plot for you the function, let's go to 10. You see it looks like this. So you can see quite clearly that this pattern will never repeat. So that it's fatter at the origin here because of the x squared function. And so it's not a periodic function. These oscillations, though they look slightly quasi-periodic, they're never going to repeat precisely. And you can prove it by just checking whether it's possible that x plus L squared is equal to cosine of x squared. And for that to be the case, you would need x plus L squared to be x squared plus some multiple of pi. Suppose 2n pi. Okay? And then you solve both sides, and you'll be able to show that this can't be done for any L, which is independent of the x. And so the cosine of x squared function, that function on the right-hand side, is not periodic. It's basically fatter at the origin, and then it speeds up as you go out like this. Okay, so there is no pattern that duplicates after a fixed number of cycles. And so because that function is not periodic, then e to the cosine of x squared, or e to the minus cosine of x squared, is not periodic either. And that's partly why I had that issue in the lecture, and I gave a very simple example, but the example I gave was a bit too simple. Okay, let's continue on. So we're going to go back now and do problem set number 8. This question on the Laplacian that we didn't quite finish, and I just want to finish it now. It's a neat question to ask you to do separation of variables. I'm going to show you the screen. I forgot to show you the screen. Okay, so we're going to do this problem set 8 question. Let's just remind ourselves. So this is problem set 8 on the heat equation. Let's just remind ourselves what the question asks. We've done a little bit of it already, so we won't have to do all the details. But essentially, what you're asked to do is to solve Laplace's equation. So this is the heat equation in 2D, and you're asked to solve for the steady state solution. So you set the left-hand side equal to 0. And the difference between, someone has asked, what's the difference between part A and part B? And the difference is that in part A, you would hand it into your tutors to be marked, and part B, you would compare with the solutions. So in part A of this question, you're asked to solve Laplace's equation. You have to remember that when you convert to a different coordinate system, so in this case r and theta, then you can't use the usual Laplacian, which is txx plus tyy. In this case, you have to convert to a special polar coordinate form of the Laplacian, which is given here. But you're going to do the same thing. You're going to set t is equal to a function of r times a function of theta, separate everything, and then solve it, okay? And so let's go back to the board. Okay, and I'll write up here just the essential details of the problem so we don't forget it. So you're asked to solve TRR plus 1 over r times TR plus 1 over r squared times t theta theta equal to 0. Okay, that reads TRR plus 1 over RTR plus 1 over r squared t theta theta, where the subscripts are the just the partial derivatives. There's some conditions for you to keep in mind. The question doesn't give you boundary conditions for this problem, but there's some conditions which are implicit, okay? So t of r and theta should be periodic. It should be 2 pi periodic, right? That's a very sensible restriction for you to have because the solution is modeled on a disk that goes from 0 to 2 pi. You should make sure that it gives you one distinct value as you go around. Okay, so the temperature needs to repeat when you go through that 2 pi cycle. T should also be bounded. So that's sort of an implicit condition as well. If this is modeling the steady state heat distribution, then you expect the heat distribution to be bounded. In most of the questions that you have in this course, we never write this second condition, just because it's implicit in the physical description of the problem. That if you have a system which has no forcing in it and you're just looking at steady state, then it should be bounded. The exception is if something is happening at the boundaries, which is forcing the system. But in this case, you assume that not to be the case. Okay, so you apply separation of variables to this problem. I'll erase this. And so you let T be, let's call it R of little r times a function of theta. R of little r times G as a function of theta. You put it into here, you separate both sides, a function of r on the left-hand side, a function of theta on the right-hand side, and then you set both sides equal to a constant. Okay? The expression that we derived last week was r squared f double prime plus r times f prime over f is equal to minus g double prime over g equal to a sigma. Okay? So this just results from when you substitute this into here and you separate both sides. Aha. Do I want to use f or g? I'll use an f instead. Thank you. So I use f of r and g of theta. Thank you. Okay. Now, now you have to go through the different cases of the sigma. Okay. And let's just look at the equation for g firstly. So I'll do that now on the left-hand side. So the equation for g gives you minus g double prime. So g double prime is equal to minus sigma times g prime, minus sigma times g. And then you have the different possibilities of sigma equal to 0, or sigma positive, or sigma negative. For the moment, let's just consider sigma to be greater than 0, and then we'll go through the other two cases. So if sigma is greater than 0, then that tells you that g of theta is going to be one constant. So I'm going to call it c. Let's call it a times cosine of root sigma times theta plus b times sine of root sigma times theta. Okay, so if sigma is positive, I think I wrote that here. Okay, but depending on what the argument here is, the root sigma, you may not repeat every 2 pi. So we wrote down that condition that I've erased, right? So you need your function to repeat every 2 pi because this is modeling a disk. Okay, so in order to be 2 pi periodic, right? You need your root sigma to be basically a multiple of an integer, right? Or sigma to be equal to n squared. Okay, so under that restriction, these functions g will work on the disk, and that basically concludes this case of determining g for the sigma greater than 0. Okay. So I'm going to write that here. So if sigma is greater than 0, then we have g is equal to, we call it a times cosine of n theta plus b times sine of n theta, like so. Okay? So now you have the sigma equal to 0 case, and in the case where sigma is equal to 0, then the g function here, g double prime, is equal to 0. So if sigma is equal to 0, you have that g double prime is equal to 0, you integrate it twice, and you have a linear function, so we're going to call it a of theta plus b. A theta plus b. Okay? But g has to be 2 pi periodic, right? The g function has to repeat itself every 2 pi, and this is a linear function, so that's never going to repeat. So the only way this is 2 pi periodic is if a is equal to 0, and hence b is equal to a constant. Right? But a is equal to 0 for the periodicity, right? And so that tells you that g is basically constant. Okay? So if sigma is equal to 0, g is equal to, we'll call it b for the constant. Okay? Just so you can imagine what this looks like, if you're not used to imagining these problems, the point is that you have a disk. Okay, some disk of radius a, and you're trying to find the heat distribution in that disk, right? And so g is basically keeping track of the temperature as you go around an angle, because that's the theta dependence of that in this expression. F here is keeping track of the temperature as you go outwards like this. So F here is telling you how the temperature varies as you walk out from the origin. Okay, this function here is, if this a were not equal to 0, then what that would tell you is that as your theta increases to 2 pi, this temperature is increasing, right, by this amount, a times theta. In other words, this component of the temperature is 0 at this location, but when you wrap around and you get back to the original point, you're at 2 pi times a, and that doesn't really make sense because it tells you that the heat is discontinuous at this location. So the only way that this can be a possible solution is if a is equal to 0. Okay, that's how you should imagine it. And similarly to how you imagine these two components are saying that it's possible for your heat to be expressed in a oscillatory form that is a cosine or is a sine as it walks around in the angular direction. And what's essential is that it's continuous when it gets back to the start. And so that would mean that that sigma, the root sigma, has to be n. Okay, so that's the two cases. And then you have the sigma greater than 0 case. Sigma less than 0 case. And in that case, g is a times e to the root sigma times theta plus b times e to the minus root sigma times theta. So they're exponential growth and decay solutions, but there's no way for these functions to be periodic, 2 pi periodic, unless a and b are equal to 0 and you have the trivial solution. So you would conclude that a is equal to 0 is equal to b, because it has to be 2 pi periodic. Okay, so sigma here greater than less than 0 case, g is 0. So you have the trivial solution. So there are only two cases you now need to examine for the equation for f. These two cases. Let's do the first case, the second case, because that's the easier case to do. So you next go and write down the problem for f. And the problem for f is this here. So you have r squared times f double prime plus r times f prime. And then I'm going to move this sigma to the left-hand side. I have a minus sigma times f equal to 0. I've multiplied both sides by the f and then moved it over. Okay? So let's do the case that sigma is equal to 0. If sigma is equal to 0, then I have r squared times f double prime plus r times f prime equal to 0. Okay? So you can separate both sides and then just integrate upwards. There's two ways of doing this differential equation. You can do it by integrating factors, or you can move it over to the other side. Let's just move it over to the other side. So we'll move it over to the other side. We have f double prime is equal to, we'll have a minus r times f prime, and then divide it by an r squared, like this. Okay, then you move the f prime over to the left and erase it on the right, like that. And then this becomes a minus 1 over r. Like that. Okay? And then looks like you just integrate it, right? So you integrate this function, you have log of f prime. Just make sure if you take the derivative here, you get the f double prime over f prime, as you should. And then you integrate this function, that's a minus log r. Okay? And then looks like you can take the exponential of both sides. Really? I remember it being slightly different, but I'm going to keep on going until I figure out whether I made a mistake or not. So I'm this plus a constant, like this. And then I take the exponential of both sides, and that gives me f prime is equal to another constant d over r. Okay, it is right. Okay. Sorry, was that a bit too fast? So you just take an exponential of both sides of this equation. This becomes e to the log of f prime, e to the log f prime, which is equal to f prime, because e to the log of stuff is equal to that stuff. On the right-hand side, you here have e to the minus log of r. So you have e to the minus log r, which is, if you like, e to the log of 1 over r, and then e to the log of stuff is equal to stuff, 1 over r. And then this becomes an e to the c, which we've written as d. Okay? If you're confused, then just go away and try to do that yourself. So now you can integrate that function, and you have to conclude that this is d times log r plus another function. Let's call that e. Okay? So that's it. That's the final conclusion. Let's write that down here. So from this, you would conclude that f is equal to d times log r plus e. But I know that log r tends to minus infinity as r tends to 0, which is no good because it tells you that your temperature at of the disk is basically is blowing up as you go towards the origin. So the only way that your f could take this form is if d is equal to 0, because otherwise this is unbounded growth. And that you conclude that f is equal to a constant. So you would conclude that f is equal to a constant e, and so the only solution in the case that sigma is equal to 0 is that both f and g are constant. Okay? So that's it for the sigma equal to 0 case, and then you're left with the most important case, which is sigma greater than 0. Okay, so let's do that now. So if sigma now is greater than 0, then you need to know how to solve these types of problems. So this is what's known as an Euler-Cauchy type problem. And it's very easy to solve them. You're just going to say, I'm going to let f be equal to r to the alpha. I'm assuming that you've seen this type of thing before. Otherwise, I'll kind of explain it in just a very basic way of how you solve it. And then you can go away and look up that term of how to solve these equations. By the way, the trick to knowing that it takes this form, you don't memorize, Euler-Cauchy form. You just think of it in terms of the derivatives. Basically, you can recognize that this equation will, this substitution will work for this equation whenever the power of the polynomial function that shows up before the function matches the number of derivatives of the function. So here, it's a power of 2, it's a second order f double prime. Here, it's a power of 1, it's an f prime. Here, it's a power of 0, and it's f to the 0. Sorry, it's f to the 0 derivative, so the original function. Okay. So these Euler-Cauchy problems are always for linear differential equations where you have polynomials like r squared times f double prime, and the polynomial order matches the order of the derivative. Okay? And you'll see it work in a second. So now I put this substitution in, and this becomes r squared. You take one derivative of this function, that's alpha. So f prime is alpha times r to the alpha minus 1. Okay? So that's alpha, then you take a second derivative, so f double prime is alpha times alpha minus 1 times r to the alpha minus 2. And so this is alpha times alpha minus 1. And then this is r to the alpha minus 2. And you notice 2 plus alpha minus 2 is r to the alpha. That's why you need the order here to match the number of derivatives, because then the shift in the derivative here will cancel with the power in front, right? And then you do the next term. This is r times alpha. I'll erase this. R times alpha times r to the alpha minus 1. Again, r is 1 plus alpha minus 1, which is alpha, minus sigma times r to the alpha is equal to 0, and then you cancel the r to the alpha. And so you cancel the r to the alphas, and you're left with a polynomial equation to solve. Like so. Okay, so this is alpha squared minus alpha plus alpha. You're left with alpha squared is equal to sigma, but sigma in this case is n squared. For the case that sigma is greater than 0, sigma is equal to n squared. So this is equal to n squared, alpha is equal to plus or minus n, and voila. Okay? So if you didn't know how to solve these equations before, you now know. So you look at the equation, you see does the power match the number of derivatives, and then you just make a substitution, a polynomial substitution, r to the alpha, put it into the equation, and solve for the alphas. It's very similar to the way you would do it with exponentials. If this was an exponential form, then you do e to the alpha times r. Okay? So you've concluded that alpha is plus or minus n, and then now you can form a general solution. And so therefore you conclude that f is equal to, let's do c and d, c times r to the n plus d times r to the minus n. Okay? It doesn't matter whether n is positive or negative because it just reverses the roles of these two things. So we're free to take n to be 1, 2, 3, and so forth. Okay? If n is negative, then what you call c is now your d, and what you call d is now your c. Okay, now you look at this equation, and you just ask yourself, do I know anything about the coefficients in front here? Do I know anything about the c and the d? But I know that if n is basically, because n is 1, 2, 3, and so forth, then this will blow up as r tends to 0, right? Because it's like a 1 over r, or a 1 over r squared, or 1 over r cubed, right? So you need d to be equal to 0 for boundedness. Just in the same argument of, you remember this one had a e plus log r, and you need the coefficient in front of the log r to be 0. In this case, you need the coefficient in front of the term that's about to blow up to be 0. So you need d is equal to 0 for boundedness. And you're left to conclude that f is equal to c times r to the n. Right? And that's it. So this is now, I'll squeeze in here, f is equal to r to the n. Okay? Okay, that's it. So you've determined all the possible solution forms, depending on the different cases of sigma. All that's left is for us to make the final conclusion. So you would make the final conclusion that in order to solve this problem here, the separable solutions are, we can index it by an n, as we usually do. It's a function of r and theta. The f here takes a constant times r to the n. So I think we had we had c in front, didn't we? But you do the usual thing, and you take c times a to be a new constant, and you take c times b to be a new constant. So this is just r to the n, and then we can index it with an an times cosine of n theta plus bn times sine of n theta. Okay, and n basically is 1, 2, 3, and so forth. Actually, we're free to include the 0 case as well. So when sigma is equal to 0, right, you have the constant solution. So if you notice that if I stick n is equal to 0 here, the cosine becomes a 1, the sine becomes a 0, and this is just r to the 0, which is 1. So I'm left with just a 0 in front. So if I start the index at 0, I've captured this solution as well. So this is the entirety of all solutions of sigma equal to 0, sigma greater than 0, and there are no solutions if sigma is less than 0. Why does n have to be an integer if sigma is just positive? So n has to be an integer basically for these functions to be periodic. Okay, so this is a necessary condition for these functions to be 2 pi periodic. If n is not an integer, then your temperature is not wrapping around perfectly so that it works for a disk. Okay, so that's basically it. So then now to form the general solution, you would just do the obvious thing and then write this as, so if I write now this is the general solution, then I would just remove this n index, and then by linearity of the problem, I can always add together all of these components, and this is my general Fourier series solution for the problem. So for a given problem, you're now going to try to solve for the coefficients an and bn. Okay, so let's look at the problem. So this concludes the first part of the problem set. Let's look. So we've just shown that we have these separable solutions. Here I didn't write it with an an and bn, but it doesn't matter. The next part of the question is asking you to find the steady state temperature in the form of an infinite series when the temperature along the boundary of the disk r is equal to a is equal to this function here. So in the upper hemisphere of the disk, in the upper part of the disk, it's temperature of 1 at the edge. This is at r is equal to a. And at the lower boundary of the disk, the temperature is 0. Okay? Okay. So let's keep this on the board. This. And then we'll erase this here. And then now you're asked to find, you want to solve for T, solve for the steady state temperature, and the problem that you're given is one in which the disk has radius A, and you're holding the top side of this disk to be T is equal to 1 on the top side of the disk, and you're holding the bottom side of the disk to be T is equal to 0. Okay, so there's also a discontinuity of temperature at the join, but that's okay. Okay, so discontinuities in temperature are allowed for the heat equation. So you have a hotter edge on the top, a not so hot edge on the bottom. By the way, I just realized, so if I asked you this question but for a line instead, then you know what the steady state temperature is for a line, right? If I told you that if I have a bar of heat from 0 to L, where this side is held at temperature T is equal to 0, and this side is held at temperature T is equal to 1, then you know that the steady state solution is just a line, right? So it's just a line. And so the temperature moves in a linear fashion from one end to the other. This is obviously a little bit more complicated, right? Because you'd think that, oh, maybe it looks a little bit like a line from one side to the other, but it's obviously on a disk, so it can't be as simple as just a linear function. Okay, so there's not much to doing this type of problem at this point because this is just a regular Fourier series. You'll impose this initial condition, so solve for T of R theta, and I might just want to cite the final solution. So you can just see at the solutions, but I want to show you the picture of what the system looks like But the final solutions give you that an is either 0 if n is greater than 0, or it's a constant otherwise. It's 1 if n is equal to 0. And bn here is, that just takes it takes either 0 if n is even, or it's 1 over a, 1 over a to the n times 2 over n pi if n is odd. Okay, and so deriving these expressions is just a matter of basically writing down your Fourier integrals from 0 to 2 pi and then splitting it from 0 to pi, where you know the temperature on one boundary, and then splitting it on the other boundary. Okay. Let's have a look at what the solutions look like. Okay, so this is just a very quick code I wrote before. So this is going to form the Fourier series solution that we found before. It starts off at a0 over 2, and if you remember, I wrote on the board that a0 is equal to 1. So this is the 1/2 that you start off with. We're going to form 100 terms, or rather 101 terms from the sequence. We're only going to go through the odd elements because only the odd elements matter, and this is the form of the solution that we wrote down before. This initial part of the code is firstly setting the radius to be equal to 1. It sets off, it sets a series of points in R from 0 to the edge of the disk, 0 to A, with 50 points. And then it sets a series of about 100 points in the angular direction from 0 to 2 pi in theta. And what's fancy about this little code are these lines 5, 7, and 8, 5, 7, 8, 9, which is basically just making a grid of points in R and in theta. So this is R from 0 to A, and then theta from 0 to 2 pi. And then from these two vectors, you need to make a matrix, a grid of values that you can plot in X and in Y space. So that's what these next few lines do. Let me plot for you the solution now. Oh, there's no plotting command. So I'm gonna make a surface. There are different ways of plotting this. Let's plot X, Y, and the temperature U. Okay, and here is what it looks like. So firstly, if I look at top down, I'm gonna look top to the three axes here. This axis is the y-axis, this axis is the x-axis, and the height of the function that you're seeing, the height of the surface that you're seeing is the temperature, with red being hot and blue being cold. Okay, so let's just look top down because that might be the easiest view to interpret. Let's rotate the view a little bit here. So now you're looking top down on the disk. It is just a two-dimensional disk. And remember that the boundary condition is set to be 1. We can do a make command to make this look a little bit prettier, I think. I think if you do axis equal, it should make it more circular. Here we are. Okay, so the boundary at this top edge is held at temperature T is equal to 1. The boundary at the lower edge is held at temperature T is equal to 0. And that's basically it. The interior temperature is interpolating. Interpolating just means, for intensive purposes, just think that the values are going between 1 and 0. So that's what you're seeing in the three-dimensional view of the temperature. It's a bit harder to rotate this. Okay, here we are. Okay, so in the three-dimensional view, you're seeing this smooth transition of the temperature everywhere except for the edges. So the edges will jump. There's a discontinuous jump because we know that the temperature has to go from 1 in the top hemisphere to 0 in the bottom hemisphere. The absolute edges will have a jump, even though the Fourier series will be smooth, and the interior will be nice and smooth. Okay? What would be interesting if you could do it, and you can do it, but it's just a bit harder, is to study the time evolution of this problem. So this is giving you, after a long time, if you start off your disk in some state, after a long time, it will evolve to this state. And it would be interesting if you could see the evolution of heat. And that's not too hard to do. You basically have to do a separation of variables in R, in theta, and in time as well. Someone has asked, what's going on at the center of this disk? I think it's just the plotting, the way the plot works. I don't think there's anything particularly special about it. It's basically the reason why you're seeing this little dark element here is because you've set down a series of mesh points which are equally spaced in R as you walk out and in theta. So basically the points are getting more compressed. You can, if you zoom in here to if you look very closely into the little mesh elements, you see the boxes here are pretty big out in the far field, but then as you go into the center, the boxes get a lot smaller. So it's just a function of the way that you're plotting it and the way you've subdivided the domain so that the boxes get very, very small as R goes to 0. Nothing particularly special is actually happening at the origin, which you can see in the shape of the surface. Look at the surface shape. Nothing is really remarkable about that origin. Everything should be nice and smooth, as things are when you study the heat equation. Okay, so that's it for. Let me just close this display capture. That's it for this problem set. I was actually going to do problem set number 9. There's a plucked string example on problem set number 9, and I'm not going to do that because I feel like we've gone over time and everyone's tired at the moment. I do want to just flash for you where we are in the coverage of the problem sets. Okay, so we've essentially finished problem set 8. We've covered this number 4. We covered the number 1. In fact, I covered the number. When I later did the videos, I realized I covered number 1 twice. I covered it at the end of one lecture, and then I covered it again at the start of another lecture. And we've also covered the sketches of question number 2, and question number 3 was left to you, but this was done in various lectures. Okay, so at this point, we're all happy. Hopefully, we're all happy with problem set number 8. And then we move on to problem set number 9. We covered problem set number 9, number 1 in one of the lectures. And we haven't done problem set number 9, number 2. This turns out not to be a long question. It's just that the integration for this problem is actually really annoying. And so I'll do that at the start of the Thursday lecture. And then we'll begin to move on to the material for question 3. So that's about it. Here's my dog if you're interested. He was coming up. That's about it for this lecture. That's about it for this lecture. I'll see you otherwise on the Thursday class. We'll do that again at 10:15, and we'll begin to cover this new material on D'Alembert solution. So my intention is to cover D'Alembert solution, and at some point I'm going to do the math of music lecture, and then we'll go and do the uniqueness. We'll do the uniqueness bit last in the course, and that'll basically be it. That'll be the end of the course. Otherwise, have a good Tuesday, and I'll see you soon.